All right, so like I said, we're kind of shifting gears here from looking at hypothesis testing for proportions to doing means with known variances. I put up this flow chart back in standard 19 when we were doing confidence intervals. We used either a z-score to record the margin of error or a t-score to record the margin of error for a sample, and then make an interval estimate where we think the actual population parameter would lie within. We use z and t scores to do hypothesis testing as well, and sometimes it can be kind of tricky on when do I use a z-score for my test statistic or when do I use a t-score for my test statistic. So here's that same flow chart on when to use which distribution. I want to use the t distribution or the z distribution. When we were looking at hypothesis testing for proportions, for percents, we always use z-scores. Rule of thumb is for proportions, you're always going to use z. When you're talking about hypothesis testing and confidence intervals, or means and averages, it's a little bit more complicated. Based off of the smaller sample size, I could have larger amounts of error. Larger amounts of error mean we have to use a t-distribution as a more conservative estimate of the population. Sometimes we could also use a z-distribution. Given a large enough sample size, the t-distribution is almost identical to the z-distribution. What's kind of that magic number to hit? Given what sample size does the t-distribution look a lot like the bell curve of the z-distribution? 30 is kind of that common convention. Given a large enough sample size of 30, both the z and t distributions are pretty much the same. Another way to think of this when it comes to hypothesis testing is to talk about the overall variability. Am I given the population variance, or am I using the sample data as an estimate, the sample standard deviation as an estimate of the overall variance? When using hypothesis testing for means, you're either going to be given the entire population standard deviation. Do you have the known variance of the population? Do you have the notation sigma? Sigma stands for the population standard deviation. Because you have the population parameter sigma, there's less variability, you have less error, and you can use a z-score to conduct your hypothesis test. Given a population parameter, knowing the variance of the entire population, there's less variability because I have that actual data. I can use z-score. If I'm estimating that variability with the sample standard deviation, if I have S as opposed to sigma, I take a sample of data, and the best I can do to estimate the variability is record the standard deviation from my sample. If I have unknown variance for the population, there's more error. I need to use a more conservative estimate for the distribution, and we have to use a t-score. Does that flowchart look familiar to you? Maybe been a couple weeks since we did confidence intervals. Kind of rule of thumb, proportions, you're always going to use z. For means, you are either estimating the variability or you're given the variability. You have an estimate, you got to use a more conservative distribution, the t-score. You have the known variance, the known population standard deviation, you use a z distribution for your hypothesis test. So let's do this. I've got a hypothesis test for us to work through, and then a confidence interval for us to make based off of the sample data recorded from the hypothesis test. ATMs, cash machines, must be stocked with enough cash to satisfy customers making withdrawals over an entire weekend, right? The bank closes on Friday. They don't get back open until Monday. They're going to have to stock the ATM with enough cash to last that weekend, right? If too much cash is kept on hand in the ATM, unnecessarily, the bank is foregoing the opportunity of investing and earning interest. You don't want to have cash just sitting around. So they can also just reinvest it. So they don't want to put too much cash in the ATM. Suppose a particular branch is expecting an average amount of money withdrawn from the ATM per customer over a weekend is $160. So on average, we're estimating that the bank will use $160 per customer withdrawn per weekend, and a standard deviation in that average of $30. If a random sample of 40 customers is examined and the average withdrawal is $172, is this enough evidence to believe that the average withdrawal per customer is no longer $160 at a 5% significance level? 5% error. Let's read through the back half of this and think about which of these different values represent what. Suppose that a particular branch, the expected average amount of money withdrawn from the ATM per customer over a weekend is $160. This $160, does that refer to the population or the sample? Is that all customers or some of the customers? All of them. So this would be U. Mu would be the population mean. The average ATM withdrawal amount over the weekend per customer. This standard deviation amount of $30. Is that the standard deviation of the population mean, or is it the standard deviation of the sample mean? Does it refer to all or some? All. So this would be sigma. Based off of previous ATM usage, we expect each customer to withdraw $160 on average with a standard deviation of $30. Now I take a random sample of 40 customers, so a sample size of 40, and their average withdrawal amount is $172. This 172, does that refer to some of the ATM's customers or all of the ATM's customers? Is that the sample mean or the population?
Sample.
Sample. So that notation would be what? What's the
X
notation for
bar.
sample? X bar. You see how these two numbers are different? Is that difference significant? Is this enough evidence for us to assume something new about the withdrawal? Or is this difference just accounted for by normal sampling variability? That I just find 40 customers and it just so happens that their average is a little bit higher. Is this difference statistically significant? That's what we're trying to prove by our hypothesis test. We have an allotted error. I want to reject the true null hypothesis. Alpha equals 5%. Let's run through some of the steps for the hypothesis test. It's the same steps. We're going to check some conditions first. Since we're talking about means, the conditions are similar, but with a few minor differences. What are some of those conditions for inference on means? It's got to be a random sample. That I randomly select customers, or is it a sample bias? Just random customers? Either. All right. Less than what?
10%.
Right? Less than 10% of withdrawals. Would 40 customers be less than 10% of the withdrawals that the ATM is making? So that's a reasonable assumption for us to make. It's the last one.
And greater than.
The last one's the one that's a little bit different than the inference conditions for proportions.
Isn't it? It
Greater than 30, or the population is normal to begin with. Right? By central limit theorem, if our sample size is large enough, over than 30, that sample distribution is normal. Or, if I have a smaller sample size, I need to make sure my population is normal to start with. So any sample I take from a normal population is normal as well. Since we have a sample size of 40, we can proceed. N is greater than 30. Our sample size is large enough to assume a normal sampling distribution. Part 2. Let's define the hypotheses for our hypothesis test. It's the ho and ha, H naught, H sub n. Since we're talking about means, we're no longer using P for proportions for our hypothesis test. We're using the parameter mu. What would the null hypothesis be if there is no difference between the population and my sample? What would their average amount of money taken out still be?
160.
So we're going to assume that they're still taking out 160. What are we trying to show as a result of this sample data?
And it doesn't.
No longer 160 bucks. How do I rephrase that for my alternative hypothesis?
U does not equal. Okay.
That tells me a lot about how I'm going to proceed. Is this either a 1 or 2 tail hypothesis test?
2.
2. You bet. be more than 160. It could be less than 160. They don't want to stock too much cash, right? Yeah. They also don't want to stock too little. Not have enough for their customers over a weekend. Unhappy customers. We're going to set up a rejection region. Am I using a T distribution or a Z distribution? Do I have the population standard deviation, or am I estimating that by the sample standard deviation? I know the overall variability, the overall variance of the population. There is less error. I can get away with a Z distribution. Estimating that using my sample data, if I have unknown variance, I need a more conservative distribution. Use the t-score. So if I draw a bell curve for my Z distribution, I have two tails. 95% in the middle, with 2.5% from the 5% allotted error, split up evenly for each of the two tails. On your formula sheet, what are those critical scores for Z that define our rejection region? 196, plus and minus 196. So positive 196 for the upper right tail and negative for the lower left. If I can take my sample data and calculate a test statistic that's more extreme, either further from 0 than plus or minus 1.96, we have significant data. We have statistically significant results. To say that the population is now different, we would have stopped. Go to the back page. Let's figure out which formula I'm going to use. On the back page, we have all sorts of different hypotheses and hypothesis test statistics for the rest of our time together this year. We talk about proportions or means. Means. Let's see, means. Is it two means or one mean? Am I taking one sample or two samples? One sample. I take one sample of data and I compare it to some benchmark. The previous estimate of $160. I take my sample, I record the average from that sample, I compare it back to my benchmark. I have one set of sample data. This is a one sample hypothesis. I'm not doing two means. I have either a z-score for means with known parameters or a t-score for mean with unknown parameters right below. Which one do we pick? I want to use a z-score or a t-score.
The z-score.
Yeah. What's the only difference between these two formulas? The only difference between these
Known
two
parameters and
sigma versus S. Known variability, unknown variability. Using a z-score or using a t-score. We've already talked about the fact that we have sigma, an estimate of the population standard deviation for the Z. We have known variability, known parameters. So for the last half of the standard 21, we're doing means with known parameters. We're using this z-score. X bar minus mu, the difference in the two means, the difference from the average, in terms of the standard deviation given by sigma over square roots of n. That basically finds the probability of our finding a sample, if it's actually true, that the customers take an average of $160 out. Got all that information recorded over here. So let's just plug and shove. 172 minus 160. The difference in the two means in terms of the standard deviation, given by sigma 30 over the square roots of 42. Once again, make sure you got it. Why am I choosing the top formula as opposed to the bottom? We have sigma as opposed to X, right?
Yeah.
Have the information that fits this formula, not this. 172 minus 160 divided by 30 over the square root of, what was it, 42? No, 40. Yeah, 42%. .30 over root 40. About 2.53. My withdrawal amount from the sample of $172 represents 2.53 standard deviations above the average withdrawal amount of $160. Based off of that z-score. Compare it back to your rejection region. Is 2.53 further from 0 than plus or minus 1.96? Is this z-score more extreme than plus or minus 1.96? Yeah. So what should our decision be? About right there. I got a red marker that works. Do we either reject or fail to reject? Okay, reject. I have a z-score that's more extreme, more positive than 1.9. We could also make that same decision by calculating the p-value. Yesterday, I had you guys practice writing your own definition of the p-value. How did we call that yesterday? What was the definition of p-value? You got to know for your next clean twists. What is your p-value in your own words? Regress hypothesis. P stands for probability. It's the probability of. So it's the probability of a sample, or a sample more extreme from what Kyler just said. Finish the rest off. Probability of a sample or sample more extreme if
The null hypothesis is true.
the null is true. If the null hypothesis is true, if the probability of us finding 40 customers that have an average withdrawal of $172. If it's actually true that the average withdrawal is still $160, it's the probability of us finding 40 people and their average withdrawal amount is $172. What's the probability of me recording this z-score? So on your z-table, let's look up that value. Why don't you go ahead and look up a z-score of 253? Where is that at? Z-table 253. 0, 1, 2, 3. Hey, 9943. Was that our p-value? Why not, Cole? You're shaking your head no. I want the right tail, right? I want further extreme, further from 0, further into the right tail. P-value. What's the probability of a z-score greater than or equal to 2.53? I take this number and I subtract it from 1. What's it going to be? 0.0057.
Yeah.
I still wager my p-value is not correct. By double, okay? Two-tail. This is just extreme in one direction. If the average amount of money increased, couldn't it also have decreased in the other direction? So since it's two-tailed, double the p-value. .0.0114. If it were actually true that the customer withdrawal amount was $160, I'd find 40 people with their average withdrawal amount about 1% of the time. If my significance level is 5%, I want to reject a true null hypothesis only 5% of the time. Is this value within the allotted error? Is my p-value less than within my significance level? So what should the decision be? When using p-value? Rejects. We make the same decision by using critical z-scores here as well. Absolutely. Reject. H0. We have statistically significant evidence. If I've rejected a true null hypothesis, I've only done that about 1% of the time. So we're within our allotted significance level, our allotted type 1 error level. Frame your conclusion. This is a significant result. The evidence has shown what? We're going to convict here, in other words. Evidence has shown what? The evidence suggests the average withdrawal is no longer $160 per customer. That's probably great. So based off of that, the bank might say, all right, how much money should I stock the ATM with? That leads me into my next question. Let's make an interval estimate based off our sample data of the average withdrawal amount. We practiced confidence intervals back in standard 19, so let's do some review there. I want to make an interval estimate, a 95% confidence interval, for the average withdrawal amount per customer over a given weekend. All of those confidence interval formulas are on your formula sheet on the other page. So flip it over. We have two formulas for means. Confidence intervals for means with known parameters, or for means with small sample sizes and unknown parameters. Which one would you use? Are we using z-scores against them?
Yeah.
You do it then. Take this formula, find your margin of error, add and subtract from your sample mean. Tell the bank how much money they should probably be stocking their ATM with. Practice the confidence interval. We have an upcoming reassessment from standard 19. These scores, you're using this formula. Confidence intervals. R plus or minus D. This one. So let's see. I'm doing a confidence interval. What's our little confidence?
This one.
You should have 1.96 standard deviations to capture 95% of the distribution, right? Adding on 1.96 standard deviations captures 95% of a region of our bell curve. Create and interpret the confidence interval. Amount of monies to stock per customer pays. Confidence interval should be approximately that. Take your sample estimate plus or minus the margin of error. So X bar plus or minus how many standard deviations. You need to add on to be 95% certain we captured the proportion.
Yes.
Look up those z-scores here. Your z-scores are all on your formula sheet. We're using two tails, 95% confidence interval, 1.96 standard deviations from the center. Captures 95% of a region. What you added, subtracted the margin of error, your maximum difference between your sample estimate and the actual average withdrawal amount. The ATM. So about $9.30, $9.30. The margin of error. I added, subtract $9.30 for my estimate. 162.7. Left endpoint 181.30. What does that mean? Interpret what you just did.
You're 95% confident that the money withdrawn from the ATM on the weekend falls between 162.70 and 181.30 on average.
Looked. To interpret your confidence interval, you're 95% confident. Each customer withdraws on average $162.70 and $181.30. Compare their previous average of $160. They expected $160 on average per customer. Is that within your interval?
No.
Is $160 within your interval?
No.
No. No, sir. Which is why we also rejected the null from earlier. Since $160 is not within my confidence interval, I would also have failed. I would also have rejected the null hypothesis in that case too. The average withdrawal amount has shifted to be above $160. $160 is not within our estimate based off of our confidence intervals. Okay. Outstanding.